space and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. If you thought Saturn was the only ringed planet, think again.
All 4 of the giant planets orbiting the Sun have ring systems.
Even Pluto might have rings.
Flying a spacecraft through them would be deadly.
These particles orbit Saturn at 15 times the speed of a rifle bullet.
So to find them, ring hunters must push technology to the limit.
It was a challenge. Like taking a picture of a cat in a coal bin.
From the outer reaches of the cosmos to a surprising ring system in our own backyard, this is the hunt for ringed planets. This is the 6th planet from the Sun. Don't recognize it? That's because something's missing. Without its iconic rings, Saturn would be just another planet. They are the key to its beauty.
The exhilaration of seeing Saturn's rings through the telescope can't be overstated. It is just such a marvelous sight.
People have been in awe of Saturn's rings since Galileo first discovered them in the year 1610. Since then, astronomers have applied everything they know about the original ringed planet in their hunt for more. But when we gaze at Saturn's rings, what exactly are we looking at? The perfection viewed from Earth masks a scene of chaos.
Things are bumping into each other and spattering off of one another, and so it's a very sort of chaotic, icy rubble field all moving together around Saturn.
Over time, ring hunters found not just one ring, but a series of 7 main bands around Saturn's equator.
The first really detailed views of Saturn's rings came from the Voyager spacecraft around 1980. And those photographs were truly breathtaking.
Each ring is made of trillions of particles, ranging in size from a grain of dust to something as big as a house. They were easy to see since they're the brightest rings in the solar system. They glisten because they are so tightly packed, and because the chunks are highly reflective, being almost 100% ice.
If you were positioned below Saturn's rings, but a few hundred yards away, you would see this vast expanse of boulders and ice balls, snowballs, and through some parts you could see stars on the other side, but other parts would be so thick that they would be opaque. It would be a wonderful sight.
Astronomers named the 7 main rings simply by the letters of the alphabet, but in the order they were discovered. A, B, C, D, E, F, and the last, detected in 1980, G. All told, ring hunters had found a system that sprawled a whopping 180,000 miles in diameter.
The rings from edge to edge are almost 2/3 or so as wide as the distance from the Earth to our own moon. So they're quite vast.
Yet incredibly, the rings form a single plane that is wafer thin, averaging less than 30 feet.
They're very flat. It's like a sheet of paper the size of Central Park.
But these beautiful structures are also turbocharged hellions. Their icy particles scream around the planet at up to 53,000 miles per hour. Like speeding cars on a never-ending cosmic racetrack. At these high velocities, the rings spell certain death for anything daring to venture too close.
These particles orbit Saturn at 15 times the speed of a rifle bullet.
A chunk just 2 inches wide could blast a deadly hole in a spacecraft. the particles are like race cars at mind-bending speeds. Yet like these cars, each particle in the ring is moving at almost the same speed as the ones around it. But since their speeds and directions don't match exactly and are sometimes changed by forces around them, the icy chunks relentlessly bump and jostle, just like race cars in the heat of competition. Most bumps are low impact and don't have much effect. But at times, a crash can send a particle hurtling into space. What keeps these rocketing ice balls in a ring? The powerful force of Saturn's gravitational pull.
If you suddenly took Saturn's gravity away, then the ring particles would go flying off in the directions that they were going at the moment that Saturn disappeared.
Instead, the gravity of the planet and the velocity of the particles are in perfect balance, so that the particles are eternally falling or curving in towards the planet, but never getting any closer. But Saturn is not the only source of gravity. The particles in the rings have their own. And it is relentlessly trying to pull them into a cluster to form something larger, like a small moon.
Every particle is attracted to every other particle, and the more massive ones have a bigger pull, and the closer you are, the more the pull is.
But the gravity of the particles works against the gravity of Saturn. It's an eternal war.
There's this constant battle, if you like, between the force of gravity trying to pull things together, gravity of the ring particles, and Saturn's gravity trying to tear them apart.
Saturn's gravity pulls particles away from each other because of a universal law about the speed of objects in orbit.
The closer you are to Saturn, more quickly you need to move to stay in orbit. If you're not moving really fast, you'll fall into the planets.
Particles of Saturn's innermost ring tear around at more than 30,000 miles per hour faster than those in the outermost ring. Even if one icy chunk is just a foot closer than another, there will be a tiny difference in speed. That difference is enough to prevent the particles from staying together.
Even over very small distances, the inside particles are moving faster than the outside particles, stretching them out along these ring arcs. So you'll never get the rings coalescing back into a solid body.
This perpetual battle of particles grouping into small structures, being pulled away and regrouping, has maintained the rings for millions, possibly billions of years.
They're sort of jostling each other and bumping into each other, feeling their own very, very weak gravity, continuously forming transient structures which come and go. The whole ring system is in a very nice balance.
The balance of gravity holds the ring system in place, but it's the motion of spinning around the planet that creates their breathtaking form.
We've come here to a pizzeria to show how the natural form for a very rapidly rotating object is a thin disc. So we're starting out with a piece of pizza dough that's not spinning and is pretty much a round lump. When the dough is thrown and is spun up, it naturally flattens out into quite a very thin disc-like shape.
The centrifugal force from the spinning causes the dough to flatten out.
For a similar reason, the rapid orbital motion of the particles in Saturn's rings, the spin, if you will, of Saturn's rings, allows it to form into a very stable, very long-lived, extremely thin disk.
But if the rings are so stable, why did they disappear 2 years after the first ring hunter, Galileo, discovered them? In 1610, he made his first observation of the rings, which through his primitive telescope appeared as circles on either side of the planet. When he looked again in 1612, the circles were gone. Galileo was baffled, but the answer to this mystery is obvious to modern astronomers.
Galileo didn't see these protrusions the second year because at that time, Saturn's rings were nearly edge-on to his line of sight, and so they were essentially invisible.
An edge-on view occurs twice in the 30 years it takes Saturn to orbit the Sun. The angle at which the rings are seen is constantly changing because the planet itself tilts 27 degrees.
So this is a Saturn, and it's tilted 27 degrees, so it's facing me. I can see the rings from above. Saturn moves, so now it is here, and I could see the rings in profile as a straight, thin line. Then it moves on the other side, and you can see the ring from down below.
While Galileo's mystery was swiftly resolved by later ring hunters, one of the most fundamental questions about Saturn is hotly debated to this day. Where did the rings come from?
It's the biggest conundrum in ring science, really, the origin of Saturn's rings.
Two theories vie for dominance. One holds that the rings formed just after the birth of Saturn, 4.5 billion years ago. They were the leftovers from the spinning disk of material that became the planet. The second theory puts their age at just 100 million years, a relative newborn.
If the dinosaurs had telescopes and looked up at Saturn, there might not have been a ring system there. It's probably much newer than that, but we happen to be the lucky ones that the rings are there at the same time that we have the technology to explore them.
The belief is Saturn's rings were created by a cataclysmic event. But was it a massive collision between a moon and an asteroid? Or an invisible force that ripped a moon into billions of pieces? They are some of the most awe-inspiring structures in the solar system. Wider than 22 Earths, while only 30 feet thick. But the biggest mystery facing ring hunters is how Saturn's rings got there. Many believe that the rings were born when one of Saturn's moons was ripped to millions or billions of pieces by a powerful force called tidal effect.
Tidal effect is any gravitational interaction where one side is getting tugged on more than the other side. So if I had a big, massive object right here, closer to this shoulder, it would pull more on this shoulder than this one, which is further away, and it could pull me apart.
In a black hole where gravity is violently strong, tidal effect could pull apart something as small as a human.
If you've heard the phrase spaghettification, the black hole is pulling on your feet more than your head, and it's stretching you out into a long strand of spaghetti.
In less extreme places, like our solar system, the impact of tidal effect is only felt by large bodies like planets and moons. Anyone who has gone to the seashore has witnessed the moon's tidal effect on the Earth.
The part of the Earth that's nearest to the moon gets pulled more strongly toward the moon than the far side of the Earth. So the Earth takes on this bulgy appearance, so you can see at the shore that the water goes up and down over a roughly 12-hour period.
But the moon's tidal effect doesn't only pull the oceans, it pulls the entire planet.
Something that's not often recognized is that the rock ball of the planet itself changes shape as well. In fact, Earth's diameter in the direction toward the moon is a foot or two longer than the diameter in the perpendicular direction, because the whole Earth is stretched toward and away from the moon.
Planets also have a tidal effect on their moons. In fact, since planets are larger than moons, they have more gravity and create stronger tidal effects. Our moon is made of rock and metals, far too solid to be ripped apart by Earth's tidal effect. But some of Saturn's moons were loose conglomerations of ice, dust, and rock, sometimes called rubble piles.
The rubble pile might be like a snow cone or something like this, you know. It's put together with no strength except just little surface forces, so very, very low strength object.
Some scientists believe one of these moons strayed too close to Saturn 100 million years ago.
The loosely held moon would get ripped apart into thousands or millions of pieces of a wide range of sizes. And they would have different distances from the planet and thus would take on different orbits. The different periods of the different orbits would gradually spread the stuff out into a ring system.
Only further exploration can determine whether the rings of Saturn were created by tidal effect, the destruction of a moon by an asteroid, or from leftover debris when the planet first formed. But astronomers recently discovered particles joining a ring right before their eyes. They found that Saturn's outermost band, the E ring, only exists because of violent upheavals on one of Saturn's moons called Enceladus. What erupts from this extraordinary moon is water.
That water squirts out in geysers and instantly freezes, kind of like the water in snowmaking machines at ski resorts.
These plumes of frozen particles shoot hundreds of miles off the surface of the moon, where they enter into orbit around Saturn and form the E ring. Besides the unexpected thrill of seeing material added to one of Saturn's rings, astronomers discovered another surprise locked within the microscopic particles of the E ring. In June 2009, scientists found trace elements of chemicals commonly known as salt and baking soda.
The thing that's so exciting about finding both the salt and the carbonates in the E ring is that those are the kinds of things that suggest a liquid ocean inside of Enceladus. And just like on Earth, where life formed in the oceans, we believe, it could very well be true that life is formed inside of Enceladus. This is a really exciting possibility, but it's by no means solved because we don't see the sodium in the plume coming out. These observations suggest some other explanations. We don't know. We have to keep exploring.
Astronomers are in fact getting streams of new data on Saturn and its rings every day from a spacecraft launched in 1997 called Cassini.
Cassini is about as big as a small school bus. It's the biggest interplanetary spacecraft NASA has ever built.
After a 7-year journey, Cassini became the first spacecraft to enter into an orbit around Saturn, giving mankind a front row seat to the 6th planet from the Sun and its rings.
Already it's gone over 100 times around Saturn. By the end of the mission, it'll probably have gone around Saturn 200 times.
Cassini has captured images closer than ever before, revealing a wild world of shifting forms and surprising variation.
From a distance, it almost looks like the rings are a solid body, just a sort of stately march around the planet. But it's not that way at all. It's a very chaotic, messy process.
Studying rings used to feel like we were studying geology, and now it feels more like we're studying the weather.
To the astonishment of astronomers, Cassini revealed particles in one ring forming a towering wave. First seen in 2009, the wave rose at the edge of a ring to the terrifying height of more than a mile.
The rings themselves are very thin, only about 30 feet, so it's as though you were on a shallow lake, only 30 feet deep, and then a mile-high wave comes right at you. It's really remarkable.
The cause of this planetary surf turned out to be the gravitational effects from a moon just 5 miles wide, named Daphnis. Because it's so close to one of Saturn's rings, the gravitational pull of this tiny moon is strong enough to create the gigantic waves.
It shows how kind of powerful and remarkable these gravitational interactions are between the moons and the rings.
These waves are only one way that moons put their mark on rings.
They also add to the shapes of the rings so that you get gaps and edges and very clear divisions between the rings.
Moons that create these edges and divisions are called shepherd moons. In Saturn's F ring, there's a moon on each side that actually herds the particles into the ring. These moons, Prometheus and Pandora, are in essence Saturn's cowboys. They work just like cowhands you'd find on a ranch.
All right, let's go.
All right.
Let's go get them. Get.
What we're doing here is much like what Saturn's moons do to Saturn's rings. We're herding them just like the moons shepherd the rings. For example, Prometheus and Pandora herd the F ring. I'm like Prometheus, I'm on the inside and my partner is on the outside, that's Pandora. And we're keeping these cattle in line just like the moons keep the rings in line. When a moon interacts with a ring particle, it can kick it into a higher orbit further from Saturn or kick it into a lower orbit closer to the planet.
Pandora, being further from Saturn, orbits more slowly than the particles in the ring. If a particle strays out, Pandora's gravity pulls on it. This slows the particle down, causing it to fall back to the ring. On the inside, Prometheus orbits at a higher speed than the ring particles. Its gravity pulls them forward, increasing their energy and causing them to move away from Saturn. The overall effect is that the two moons confine the particles between them, creating a sharply defined ring.
The moons play an enormous role, a very fundamental role in the way the rings look and how they got formed. The moons can shepherd the particles in the rings so that you get gaps and edges and very clear divisions between the rings. So the rings are completely dominated by the moons from the beginning to the end.
The glittering bands of Saturn sparked a quest for more rings. Yet they were the only known rings for centuries. Ring hunters dreamed of finding others, suspected there were more, and yet could see nothing visible like Saturn's. As the 20th century waned, a small team of astronomers focused a telescope on Uranus in hopes of learning about its atmosphere. They weren't ring hunters at all, and yet their mission led to a shocking revelation, triggering the biggest discovery in rings in more than 300 years. Ever since Galileo discovered Saturn's brilliant rings centuries ago, the quest for more rings was on. Yet hundreds of years rolled by without another discovery, to the enormous frustration of ring hunters. So in 1977, when a small team of researchers staked out the planet Uranus, their sole interest was its atmosphere. On March 10th, the team flew a modified jet to the edge of Earth's atmosphere and trained their telescope on the seventh planet from the Sun. They were waiting for the moment when a distant star would pass behind Uranus.
They were measuring the brightness of a star as a function of time as it was going to pass behind the planet. And in this way, you can study the structure of the atmosphere of the planet.
But as the star approached Uranus, something strange happened.
Before it went behind Uranus, the light actually blinked out several times.
Stunned scientists waited to see what would happen when the star reappeared on the other side.
And then after emerging from behind Uranus, it blinked out several times as well.
The team had discovered something completely unexpected. The dips on one side of the planet were perfectly symmetrical to those on the other. It meant they had found a second planet with rings.
That was a surprise and it was very exciting to see for the first time.
It was the first new ring system discovered in more than 350 years, and it would open the floodgates. Two more ring systems would soon be discovered, one on distant Neptune and one on the largest planet, Jupiter.
So we now know that 4 planets in our solar system have rings. And in fact, all 4 of the giant planets orbiting the sun have ring systems.
But if rings are common, why did it take astronomers so long to find the others? Because the rings of the other planets are quite different than Saturn's.
It wasn't by accident that Saturn's rings were discovered back at the beginning of the 17th century, and no other ring system was found until near the end of the 20th century. Saturn's rings are broad, they're bright, they're spectacular. The other systems are much more subtle.
Subtle in part because of their size.
A very surprising aspect of the discovery of Uranus's rings was that they're very narrow.
Most of Saturn's rings are thousands of miles wide. By comparison, the majority of Uranus's rings cover less than 2 miles.
The other part is that they're very, very dark, whereas the rings of Saturn are made of ice and they're very bright. Think about something much darker than tar. They're as black as anything you can probably see.
What's more, the outermost rings of Uranus are so dim, ring hunters didn't find them until 2003. This is largely because there is almost nothing in them.
Throughout the system, there's clouds of very faint dust at this level of a filling factor of 1 in 100,000 or 1 in a million.
These particles are spaced so far away from each other, it would be like a cosmic racetrack that stretched from the Earth to the Moon and back, and it would have just a handful of cars on it. It's a radical difference from Saturn's rings, where particles are often packed in side by side, bumper to virtual bumper. The outer rings of Uranus are extremely sparse, but they are not the faintest. That award goes to the outermost bands around the 5th planet from the Sun. Mighty Jupiter has the most delicate rings of all. So far, astronomers have identified 4 ethereal rings circling the planet: an inner ring, the main ring, and 2 outer rings. Unlike the icy chunks bigger than a car found in Saturn's rings, the particles in the rings of Jupiter are mainly the size of the finest dust.
We often refer to these as dust rings, but the better word would be smoke rings. The particles are microns in size. The smoke coming off of a fire is basically microns in size.
The rings, like the planet, are mammoth, sprawling nearly 300,000 miles in diameter. Yet incredibly, if you squashed all the particles into a single ball, it would be no wider than a football field, and perhaps as small as the distance of a first down. There is so little in the 2 outermost bands that they are the faintest rings ever detected in our solar system. Almost invisible, they are called the Gossamer rings.
You could actually sit inside the Gossamer ring of Jupiter and not even know it was there. I mean, maybe you'd hear an occasional ping on your spacesuit as a dust particle came by, but you would not see anything.
As impossibly faint as the bands of Jupiter are, it was the search for rings around Neptune that proved the most challenging for ring hunters.
Neptune was suspected to have rings in the 1980s when the material in these regions blocked the light of a star that was about to go behind the ball of the planet.
Using the same technique that had detected the rings of Uranus, astronomers tried some 50 times to find the rings of Neptune. The results were maddeningly inconclusive. exasperated scientists proposed a radical explanation. Since starlight was occasionally blocked, perhaps there were strange rings around Neptune that only partially encircled the planet.
We didn't think that they were complete rings because the blocking of light on either side of the planet was not symmetrical the way it was for the rings of Uranus.
Could it be that Neptune had some bizarre and mutant ring system? Ring hunters had never been so determined to solve the mystery, and they had no way to anticipate how bizarre that solution would be. For more than 350 years, the only known rings were the bright and dazzling bands of Saturn. Then, in a space of just 2 years, starting in 1977, 2 new sets of rings were discovered, one on Uranus, the other on Jupiter. But the search for rings around distant Neptune dragged on for many more frustrating years.
Neptune is very, very far away. It's a great distance from the sun, and therefore there's not much illumination on the ring. In addition to that, no spacecraft went by Neptune until 1989, when Voyager 2 from NASA went by the last planet in our solar system.
Voyager 2 was the astronomers' best weapon in the hunt for rings. On August 25, 1989, the spacecraft got as close to Neptune as any man-made craft ever would. It captured the best images ring hunters had seen of the 8th planet from the sun, an incredible technological feat.
It was a challenge. It's like taking a picture of a cat in a coal bin and under moonlight or something, you know.
So would they reveal that Neptune had no rings, full rings, or the mysterious partial rings that some astronomers had proposed? For more than a decade before the Voyager mission, scientists had tried to detect rings using the light of various stars passing behind Neptune. Some attempts saw dips in starlight, but they were never at the same distance on both sides of the planet, like full rings would be. Neptune was exasperating.
We knew there was stuff there, but we didn't know what the configuration was.
So when images from Voyager rolled in, ring hunters were thrilled. Not only were there complete rings, but there was something in the rings that had never been seen before. Arcs.
The most prominent feature are a set of arcs which only go less than 1/10 of the way around the planet. The rest of the ring, very ethereal.
Arcs were simply segments of a ring that were brighter and thicker than the rest of the ring. The incredibly small amount of material in the rest of the ring explained why astronomers had not been able to detect the complete rings from Earth.
The arcs lie within a full ring, but the matter in this full ring is almost transparent. So we could never see it before with watching it block starlight.
The discovery of rings around Neptune meant that all of the gas giant outer planets had rings. It was a reflection of the natural order of the cosmos, because the disk shape of rings is one of the most primordial forms in the universe.
The universe contains 2 sort of fundamental blueprints for objects, and those are spheres and disks. Spin is a really important aspect of an object structure, then it will tend to form into a disk. And so we see disks on every scale in the universe.
This is why the rings of Saturn can tell us about the origins of a much bigger ring system, the one around our sun.
Saturn's rings are a blueprint for the processes that give rise to planet formation. If we were to go back in time and visit our own solar system 4.5 billion years ago, the young sun would have been at the center, and it would have been surrounded by a disk of gas and dust. And that disk and gas and dust would have had planets forming inside of it. And that whole disk would have looked, to a certain extent, like a system of rings.
The first planets began to form in the debris disk. As they grew larger, their gravity cleared out space in their orbits. Debris that was within their gravitational influence was added on or whipped out into space.
This is exactly what happened in our own solar system when Jupiter formed, because Jupiter was massive enough to clear a gap in our own disk.
In time, the other planets in our solar system formed and cleared out their own orbits, leaving just two spaces for debris, the asteroid belt and the Kuiper belt. Together, they create what amounts to a vast set of rings around the Sun. As a blueprint of our solar system, rings help us understand our own beginnings. Yet ring hunters have long wanted to pursue one of the biggest prizes of all: ringed planets in other solar systems.
We already know of many planets that have masses similar to Saturn and composition similar to Saturn. And it's a good bet that not all of them, but some of them have spectacular ring systems.
They now believe they'll discover the first ringed planet from another solar system very soon, with the help of one of the world's most powerful telescopes, Kepler. Kepler is able to track about 100,000 stars at a time. It was designed to measure the tiniest changes in starlight, so that it could detect distant planets that pass in front of a star.
When that happens, the planet blocks out a little bit of the star's light, and Kepler can detect that dip. If a ringed planet goes in front of a star, then the rings also block out the star's light, and that signal can be measured by Kepler as well.
While Kepler gazes deep into the universe, astronomers are also hunting for a new ring within our own solar system.
3, 2, 1, 0.
In 2006, a mission called New Horizons roared off the launch pad. Its 2.7 billion-mile journey will take it to the frozen edge of the solar system. If it survives, it will become the first spacecraft to fly past Pluto. Astronomers suspect that the dwarf planet may be the first rocky object found to have rings. Yet there is another ringed planet in our solar system. Its ring is on a collision course with disaster, which could lead to chaos on Earth. The four outer planets of our solar system are all encircled by rings, some dazzling, some dusty, some remarkably faint. Yet the quest is on for one more, the most distant of all, encircling a frigid rock called Pluto. Once considered to be a genuine planet, it was reclassified as a dwarf planet in 2006. In 2015, it may become the newest member of our solar system found to have rings.
Pluto might have rings, very faint rings, or may someday gain rings, because Pluto is in a region where there are lots of comets floating around. And if one of them gets close to Pluto, it might get tidally shattered by Pluto's gravity, temporarily forming a ring.
A mission called New Horizons is already a third of the way to a rendezvous with Pluto. The images it transmits in 2015 should reveal if the distant dwarf has rings. Yet ring hunters recently expected to find a new ring system much closer, on Earth's nearest neighbor, Mars.
There's long been speculation that Mars might have a ring system. It goes actually back to the 1970s. And part of the reasoning now is that everywhere we look in the solar system that we see small satellites, there is a faint ring associated with them.
Two small satellites, or moons, orbit Mars. Though each is less than 20 miles wide, astronomers believed enough dust came off these moons to form a faint ring.
They must be producing clouds of dust. We know that for certain. And the only question is, when and how does that form into a ring?
Yet when they trained the powerful Hubble telescope on Mars in the 21st century, they saw nothing.
We've looked twice now and we have not seen anything. So we're beginning to get a little bit puzzled as to why there are no rings of Mars.
The Earth itself once had a ring. Giant chunks of red-hot rock whizzed around the planet for at least a few years, and then vanished. How could that have been? 4.5 billion years ago, when the Earth had just formed, a giant body the size of Mars smashed into our planet.
And that formed a temporary ring that was even more spectacular than Saturn's is today, in the sense that it was not just a big, thick ring, very massive, but it was glowing red hot.
As the molten rock cooled, some was thrown back to Earth and some flew out into space. The rest of the material condensed into a sphere that became our moon. But Earthlings don't need to feel left out. Our home planet has a new ring, and this one is just 50 years old. It's not made of dust or icy rock, but metals and silicon. It's a ring of satellites.
The Earth has built itself a highly technologically complicated ring of satellites that will last for millions of years.
Comprised of some 400 satellites, it's the only known ring created by life in the universe. It hovers 22,000 miles above the Earth's equator in a geosynchronous orbit, where their speed will hold them in exactly the same spot over the planet indefinitely.
The geosynchronous satellites are this very special sort of subcategory of satellites, and they form a true ring around the Earth. And it's a ring in the sense that they are orbiting particles that are continuously falling around the Earth, much the same way as Saturn's ring is gravel-like icy particles that are all falling around Saturn.
Earth's ring is a critical component to human communications, but it's heading for disaster.
And what we know in ring studies is that you put enough things in one place and they're going to start colliding.
In fact, in February of 2009, 2 satellites in a low Earth orbit did collide. The crash sent shockwaves through governments and the scientific community around the world.
We had 2 large satellites and they collided, they blew themselves to smithereens, and we now have maybe 10,000 objects all in orbit around the Earth. Each of those is a bullet, and each of those is moving perhaps at 10 miles per second, and any one of those has the capacity to take out another satellite should another collision occur.
Each new satellite in the geosynchronous orbit is like adding a race car to the track. Every one increases the danger of a collision. If 2 collide, the flying debris could destroy the entire ring, throwing communications on Earth into chaos.